Okay, so the main goal here is to, or if given two sets expressions, you prove that are equal, right? And for that, there are three methods to do that. You have your Venn diagram, you have your element method, and then thirdly, you have your algebraic method. We're mostly going to use the Venn diagram and this, right? And then at the end, we're going to do one kind of past paper question, and I'm going to leave you to another past paper to try on your own, and then post your answer in the group, right? Whichever group you're in, whether it's the small group or the bigger group. So we use De Morgan's laws. I don't know if I'm pronouncing it correctly, but we use De Morgan's laws to prove if sets are equal or not, right? So the first one is this kind of proof. So you have your x or y, and then you have this complement, and then this is equal to the complement of x and the complement of y. And we basically, I'm just going to prove this using the Venn diagram, and then at the end, we're going to show how these are equal, right? So with the first one, so this on your, to my left-hand side, this basically means take everything that's not in x union y, or that's not in x or y. And then the second one would mean take everything that's outside x and outside y, right? So for example, so to prove this first, if you have, let's say, these two Venn diagrams, so you have x and y, of course, because you're dealing with two mutually inclusive things. So you'd have maybe u, or the universe, maybe equal to p, and then here you'd have an x and a y here. And then obviously the first one is to take everything that's not in x union y, if you remember correctly. So this would mean take everything outside x or y. So it would be all these bases outside x or like this. And then maybe you have your x here and your y. And this here basically means take everything outside x and y. So taking everything that's outside x, you'd first have, let's say, that, right? And then oh sorry. And then secondly, they say take everything that's outside y. So because you've taken everything outside x, now you have to take everything outside y again. And all of that would mean this. And this shows that these two are equal, right? Hope you understood that. And then and that's how the first law is proven, basically. Moving on to the second law, so you would have this and that, and this basically means the complements of an intersection. So this obviously is an intersection, and that's a complement. So the complements of an intersection equals the union of the complements. So you would have a union and the complements, showing that these are equal. Everything except the elements in both. So you're taking everything except the elements that are in both. Intersection means both, right? And then for the second one, this basically means take everything that's not in x first, and then take everything that's not in y. So it's basically more like the same thing we did last time, but I'm going to show you how it differs here. So for example, for this first one, or it's not here. So let me write it here. So for x intersection y, okay, x intersection y, if you have two Venn diagrams like that, hope I didn't lose anyone. So the first one says take everything except the elements in both. So both x and y would be in here, right? So if we're taking everything except the elements in both, it would be all the x's, all the y's, and everything outside that. So everything outside everything in both, right? Hope you understand what I mean. So you're actually not taking this. And then if we were to move to proving how that is equal to x complement the union y, if you had a Venn diagram, or two Venn diagrams like that. So if you had that, and obviously you have to first take everything that's not in x, and that first would be everything in y. So I forgot to write my y and x. So we're taking everything that's not in x first. So it would be everything here, everything there, right? And then secondly, we have to take everything that's not in y. So because we took everything that's not in x, now we have to erase everything that's not in y. So now, remember, I hope you understand what I mean, because I'm just going to complicate things a little bit here. So at first, the yellow would mean take everything that's not in x, and now we're taking everything that's not in y, and everything that's not in y is all of this. I hope you understand what I mean. Everything that's not in y is in blue, and that shows how we are only left with the middle parts here as well. Right? And that basically is the second law proven. And now we're going to prove the double complement law. Does anyone want to explain what basically this would mean? And then I'll explain further. What do you think we should do with this?
I don't know. I don't know.
Okay. Okay, so this basically means take everything that's not in X, right? So we have an X complement. Look at this. Okay, for those. So last time we were doing sets and we did complements. So, okay, I understand if you're saying you don't. Okay, so this means take everything that's not in X because that's X complement, right? So if you have maybe, let's say, a Venn diagram like this and you only have X, this says to you take everything that's not in X first, right? And then we're done with that. And then it says again, take everything that's okay. So it first says take everything that's not in X, and then now it says take everything that's the complements of whatever you didn't take. So at first, the everything that's not in X would be all of these things, and now it says we should take the complements of all of this that I'm doing right now. So the complements of all of that would be this inside. So the complements of that would be this, right? So the complements of everything that's not in X basically would be X. So this proof simply shows us that this is equal to X by default. So anytime you're given a double complement, the answer is the initial complement that you were doing. I hope you get that, right? And then I'm gonna just ask what?
No, saying thanks.
Okay. Okay, I'm gonna brief us on the commutative laws, associative law, sorry, and the distributive law, and then we're gonna do a proof that regards us to know all of these, right? So with the commutative law, order doesn't matter. If you have x or y, you can change it to y or x. It's still the same thing. It's the same as saying 5 plus 2 and 2 plus 5. It gives us the same answer. If you have the associative law, if you're dealing with brackets and three things, more like grouping, if you have x or y or z, you can write it as like this. It's just a bracket that changes direction or position. So if you have 5 plus 3 plus 2, and then you have 5 plus 3 plus 2, the side is the same thing. You just have to know your God myth. And then the distributive law would be your x and y. And then, so you have x and y, and there's basically distributive law is you distributing x everywhere, and like you would with numbers like this, right? So that's your distributive law. So we're given here three sets, and we are asked to prove that x and then in brackets we have y or z is equal to the distribute. Can you see that this is a distributive law? So we have to prove that they can be distributive and all of them are equal. Right? So if x is 1, 2, 3, y is 2 and 4, and z is 3 and 5, let's just do a proof together, and then I'm going to give you a similar proof that's on a past paper. So obviously, if you have something like this, what you need to do, and sometimes they can tell you in the exam how to start your answer, or yeah, basically how your answer should start, or they might lead you to how your first step should look like for you to be able to continue with your other steps. So obviously, if at first you have this on your my left hand side, what I'm gonna do first is do this on the side, and then from there I'm just gonna co-join it to this, and then I'm gonna prove the distributive law, right? So if I have this, I'm just gonna write my y or z, and that's equal to, so if I look at my y is 2 and 4, and I have 4, and then my z is 3 and 5. So y or z would be 2, 4, 3, and 5, right? So now I have this part, and now I have to join it to this, and then I'm gonna do the distributive law. So now x and y or z, this is equal to, so I'm just gonna take a look at x. X is 1, 2, 3, 1, 2, 3, and then remember my y was, okay, let me write this down here. So x was 1, 2, 3, and then I have an end. My y and z, my y or z was 2, 4, 3, and 5. And if obviously you're dealing with and, you want to take everything that's in both. So everything that's in both in this case would be 2 and 3. So we have 2 here, we have 2 there, we have 3 here, and 3 there. Right? So this is 2 and 3. Okay, right? So I have now everything here. I have everything here. Now I just need to find everything on this side. And then obviously if everything here is equal to this, that means I've proven that these two are equal, right? So let me just write this as my left hand side. I'm just going to prove my right hand side. Okay, starting with x and y. So x and y would be this first, and then I'm going to do x and z at the end. So my x and y is basically x was 1, 2, 3, and y was 2 and 4. 2 and 4. So if we take everything that's in both, that would be only 2. Right? And then my x and z is basically x was 1, 2, 3, and my z was 3 and 5. Let me double check. Yes. So my z is 3 and 5. If I take everything in both, that would only be the 3. And then now this says to us we should do the union of both. So we have now x and y union x and z. This is the same as the 2 that we found and the 3, the 3 that we just found. And the union of those both would be the 2 and 3. Right? So let's check if my right hand side is equal to my left hand side. So my left hand side was 2 and 3, and my right hand side is also 2 and 3. And so therefore, x and y or z is equal to x and y or x and z. Let me check if no one is in the lobby. And that's how you basically do your proof or answer your exam question. I answer my past papers like that. I'm not sure if that's because I see other people using the if and only if and stuff like that, so I don't know. But that's how I answer. So for 5 minutes, you're going to do that, and I'm just going to move on to, you're going to send your questions in the, either the smaller, if you're in the small group, you're going to send your answers there. If you're in the bigger group, you're going to send your answers there, and I'm going to check. We might do corrections. Also, make sure you understand what the question wants from you. If they're saying A plus C, that means you have a mutually inclusive Venn diagram there. And then if you also have A or B, I think it can be mutually inclusive. Yeah, but it has to be, it can. So you can have a mutually inclusive. So just make sure you have that, and I think it'd be good. If A or B can be, I think it can be exclusive. But just try one with mutually inclusive and one with mutually exclusive. And then I think by the end, you'd be able to see which one would be the correct between the two. So actually, guys, I just did the first one. With the first one, there's 2 ways to do it. You can show me either two of those ways or one of the, and also remember our 2.3, that multiplication, that just change it to a plus sign and then follow the instructions.